Okay, welcome back, everybody. Just a quick announcement. I inadvertently forgot to change the due date for some of the activities and homework. You probably saw that I did that. I sent an email explaining that I didn't do that. They're adjusted now because, as I promised, I won't make anything due until after we complete it here in the lecture part in Zoom. So if you turned it in, okay, that's fine. If you're happy with it, no problem, just ignore the email. But if you want to resubmit, feel free to resubmit any of those assignments that need to be redone. Okay, so anyway, any questions about that? Yeah. All right, then. Well, I tell you, let us complete chapter 8, and then we'll jump on 9 and get that thing rolling. And let's see where we at. Okay, we ended up on this page, but just a quick rehash. Now, what we're doing here is the chapter is called nomenclature, okay, and it's naming the compounds, but we're also learning how to put these together, how to put the atoms together so we can make compounds. So we can also determine the structure using the Lewis-Dot method, Lewis-Dot structures that we did before. So kind of put it all together. We started with the elements. Okay. From the elements, we talked about making ions, anions or cations. And now we're talking about putting those anions and cations together to make ionic compounds. Okay. But we're also going to talk about putting these non-metal combinations to make covalent compounds. Okay, and we're going to learn how to name them. How to name them, and given the point of this chapter is given the name, give the structure, or given the structure, give it the name, back and forth. So we talked about the polyatomic ions. This is this listing of the polyatomic ions that we use as a unit. We're going to use some examples here. They have their own specific name. The important thing here is we don't change that name. That NO3, for example, that I'm showing up here in the top right corner. Let me show you that. This guy right here, all right, that's nitrate. That is the name for that species. It doesn't change, okay? We don't rename it. It's nitrate is nitrate, as the others are nitrite, sulfate, ite. Now, when we get to the name, I talked about this. I'm going to just talk about it one more time to help you out with naming these compounds and to recognize what type of species you're working with. Because if we start with just nitrogen, because we can do the same thing for sulfur, and we can do the same thing for phosphorus. But with nitrogen, we start off with the name, and obviously the atom, the element is simply nitrogen. Okay, we talked at length about it being a nonmetal. We talked about it becoming ionic, okay? And being in group 5, it will gain 3 electrons so that it will fulfill the octet on the outermost shell in its valence shell. And when that happens, it gains 3 electrons, so now it has an excess of 3 negatives, so it has a -3 charge. We change the name from that to nitride, okay? Nitride, so that's the IDE. Now, the key here is the IDE. When we hear the name, whatever element IDE, whatever non-metal, I should say, IDE, you should think the single element itself. Just like sulfide, it's just simply the sulfur, the ion sulfur. Oxide, simply the oxygen, okay? So the IDE gives you the hint as to what element or group of elements you're working with. Then what happens is nitrogen can combine with 3 oxygens and form, even though it is a covalent combination, overall, it has a negative charge in there. And this will become more clear when we do the acid-base, which is the next chapter, acid-base process. chapter on acids and bases, and it has a negative charge, okay? This is the polyatomic ion, okay? And it has its name given here is nitrate. Nitrate. Now, nitrogen can have another example of it bonded with oxygen, and that's the next one that's bonded with two oxygens and still maintained a negative charge. It is called nitrite, this polyatomic, okay? Nitrite. So note the endings, the suffix, IDE, ATE, ITE, okay? The moment you read IDE, that should tell you we are talking about the single nonmetal element and its respective charge, whatever it may be, -3 to a -1. Hence, like I said, fluorine becomes fluoride, chlorine becomes chloride, okay? The moment you read the ATE or the ITE, and the prefix starts with nit, Ni for coming from nitrogen, that should tell you the ATE and ITE, that is nitrogen, in this case nitrogen, because it's starting with Ni, it's nitrogen attached to oxygens. And it could be either 3 oxygens, giving you the NO3 -1 species, or the 2 oxygens, the NO2. Notice sulfate and sulfite, okay? This by all means is not the exhaustive list of all the possible polyatomic ions, but these are the basic common ones that we're going to use in Chem 130, okay? And so that naming here, the EN, it's the element, IDE, it is the single atom that is an anion now, okay? The ATE is that atom attached with oxygen with in this case, a -1 charge. It could have a -2 charge, look at the sulfate. And then the ITE, also nitrogen attached to, in this case, 2 oxygens. Generally, when we compare the ATE with the ITE has the most oxygens and the ITE has 1 less. Look at nitrate, has 3 oxygens, the nitrite has 2. The sulfate has 4, the sulfite has 3, okay? All right, so talked about these. All right, so here formulas for ionic compounds. Now the point here is that when we put them together, we have to put enough cations and anions together such that the overall molecule ends up with a negative, with a 0, okay? So you gotta have enough positives and enough negatives. And so here we talked about sodium. They're asking here to combine sodium with nitrogen. And this is a rehash to refresh what we did. First thing to do is to convert those elements into ions. So we need to convert the nitrogen and the sodium into their respective ions. We know sodium is a metal, okay? It is in group 1, and so therefore it would have a +1 charge. We know nitrogen's in group 5, okay? Just talking about nitrogen, we're not talking about nitrogen bonded to oxygen here. Just simple nitrogen, so it becomes the nitride. Group 5, meaning that it will pick up 3 electrons and giving us a -3 charge. So now we converted the elements given into the ions. Now at this point, we make sure we have enough of each, and we notice that we need to add enough of each to give us a net 0, okay? So I got 1 positive and 3 negative. So I need 3 positive, meaning I need 3 sodium ions to cancel out the -3 of the nitrite. So that 3 I put in front of the ion becomes the subscript for the sodium. So hence we write Na3N. And that is the formula for sodium nitrite, okay? Not sodium nitrogen, okay? Not sodium nitrogen, because we're working with the ion, the anion of nitrogen. So its name is sodium nitrite. Now, while we're doing this, you can start thinking ahead, and sodium's in group 1. So every metal in group 1, you can combine with the nitrite. Okay, so you can do the same thing with potassium nitrite. Okay, you can do the same thing with lithium nitride. We had sodium nitride we just did. Okay, and we could go rubidium nitride, everybody in group 1. Okay, because we know that everybody in group 1 has 1 valence electron. They're all going to have a +1 charge. And so look what you've done already at this point. You've got 1, 2, 3, 4 new compounds you can work with. We're going to learn that we can do a lot of mix and match. We can combine this cation with this new anion and vice versa. Okay. All right. So you're building up your database with respect to naming the compounds. Hey, it's good practice too. If you start reading your labels of the food that you eat, you're going to be surprised that you're going to become very familiar with the items that you're eating. There'll be a lot of sodium in there, a lot of potassium species in there. All right, so that's our formula, Na3N. Here, then we talked about dealing with the new elements. We got sodium, and again, which is +1. Okay, and then we got the sulfur, which again, to find out what is the anion, and this is what you got to learn, is you go to the periodic table. Okay, if you've not learned, because I was asked a question, how do I know it's a -2? Okay, the answer is this: I find the nonmetal in this particular group, and it happens to be group 5. Okay, excuse me, group 6 for sulfur. Okay, let me run through this one time. Yeah, I won't mention it again. Sulfur is in group 6. That tells you there are 6 valence electrons for sulfur. Okay, sulfur has a total of 16 electrons, and of those 16, 6 of them are in the outermost shell. Okay, the ultimate goal is to get 8 in the outermost shell. So simple math here, we need to get to 8. 6 to 8 tells me I need to gain 2 electrons to get to the 8 magical number, if you will. Okay, and so gaining 2 electrons now means that I had sulfur that had 16 protons and 16 electrons. Now it has 16 protons and 18 electrons, resulting in a net -2 charge for the ion. Furthermore, the name goes from sulfur to sulfide. Okay. You can use the F, or you'll see it also in pH. That's either one's fine, pH or the F, as far as writing the name out. Sulfide with the pH, or sulfide with the F. All right, so that's how we determine the relative charge of the ions. Okay. Now, that means here, like we did with the sodium nitride, is this: we need 2 sodiums for every sulfide. Okay, so the formula becomes Na2S. The name is now sodium sulfide. Okay. All right, the next one, magnesium and oxide. We need to first convert them into ions, step number 1. So magnesium is a group 2 element. So it becomes a +2 when it becomes an ion, specifically a cation. Oxygen's in the same group as sulfur, so it becomes a -2. And its name changes from oxygen to oxide. Okay, so now we got a +2 and a -2. this is a straightforward, I just need one of each to cancel out each other's charge. So its respective formula becomes MgO, okay? MgO, its name is magnesium oxide, not magnesium oxygen. That's totally incorrect because there's a difference between oxygen and oxide, as there is a difference between sulfur and sulfide. All right, next one. Potassium, like in sodium, it is a group 1 element. Phosphide is a group 5 element, non-metal, okay? It will pick up 3 electrons because it's in group 5. I got 5 valence electrons. It's a non-metal. It's going to gain electrons specifically. It's going to gain 3, okay, to fulfill that 8. So it ends up with a -3 charge. And therefore, like we did with sodium nitride, we're going to need 3 potassiums to cancel out the -3 of the phosphide. Therefore, the formula becomes potassium phosphide, or K3, subscript 3, okay? The important thing to remember is when we put them together, it is not K, big 3, and then P. That's not the formula. Okay, I have no idea what the K followed by a large 3. It must be a subscript. The subscript tells you that you have 3 of those specific ions. Next one, a little bit challenging. We can work it through here. Okay, step number 1 is we break both of these elements into ions. Calcium is a group 2A element. So therefore the ion is a +2. It will lose 2 electrons. Nitrogen we just did, okay, which was a -3. Now previously, this previous example is pretty straightforward. You know, it's either 1-to-1 ratio, or I need 2 or 3 of the cations for 1 anions. It's straightforward. But here we have a 2-to-3. Oh, somebody's got a question. For phosphorus, the question is, would it become phosphide or phosphide? Well, phosphide is the single phosphorus. The question is this, and I'm assuming you're talking about phosphorus. Okay, this becomes phosphide. I just saw the question there. Okay, the ITE, remember what I said about the ITE? What does that suggest? ITE or the ATE ending. That should signal that it is whatever element it starts off with, in this case, PHOSP means phosphorus. And then the ITE or the ATE would tell you that the number of, there's oxygens attached. Now, the example we had in your polyatomic ion was this one, which is phosphate. But yes, there is a 1 less, same charge, called a phosphite. Okay, so for every 8 that you see, 8, you'll always have an "ite" with it. And it's simply the difference between the two is 1 less oxygen. Notice the nitrate had 3 oxygens, and nitrite had 2 oxygens. The sulfate has 4 oxygens on sulfur, but the sulfite has 3, 1 less. Well, was that the question, Sambabu?
Yes, thank you.
You okay? All right, so now we have, let me erase this. So now we have 2 ions here. One's a +2, the other is a -3. And it could be reversed, it makes no difference, okay? But the question is, well, how do we put them together, right? Because I can't simply put them 1-to-1, because if I just simply write and I put a calcium and nitride, that wouldn't work, right? Because remember, the calcium has a +2, and the sodium and the nitride has a -3. So if I just put them together 1 to 1, the overall molecule will have a net -1 overall. Okay, and so I got to find a common number so I can put them together such that the overall number equals 0, the overall net equals 0. So a 1-to-1 relationship wouldn't work, okay? So whenever, let's say from a mathematics standpoint, what do we do when you want to add 1/3 plus 1/5? Can we add that correctly? When we have fractions, obviously, or we have 1/2 plus 1/2, right? Isn't that equal to 1, right? 2 halves equal 1. But we can't do that here. This would be incorrect to say 2/8, right? We can't do that. In this example, what do we do when you want to add two dissimilar fractions? What do you look for? Anybody? We can cross multiply, yeah. But what are we doing? We're looking for a common denominator, right? And you're correct. You can cross multiply to get a common denominator. And in this example here, your cross multiplication, you're going to convert those to 15s, right? We're looking for a common factor. So with that idea, look at what we got to do here with the +3 and the -3. What we're looking for is a common number between those two. And what will be the common number between a 2 and a 3? What number can we have that's common between those two? 6, exactly. Okay, you got it. So we need a common number, which would be 6. So I need three positive 2's, right? Because 3 times 2 is equal to a +6. And I need 2 -6's, because that is equal to a -6. And so this plus this, guess what? Equals 0. So our common number is 6, much like the cross multiplication that was stated earlier, right? So we find a common number. So I got to have enough positives and enough negatives to cancel each other out. So these numbers, these coefficients now become the subscript for those elements. So the formula becomes calcium subscript 3, nitride subscript 2. Overall, there's a +6 for all the calcium because there's 3 of them. And there's a -6 for both of the nitrides because there's 2 of them. And that equals to 0. So that is the formula for calcium nitride. Okay. And so whenever the takeaway here is whenever you combine dissimilar charges, find a common number between the two. Okay. And there's also maybe you can pick up on a little somewhat of a guideline to help you here. Let me write the formula out. There's a formula, but think about this for a second. The subscript, let me change a different color here. The subscript of the cation, okay, listen carefully. The subscript of the cation was the charge of the anion, right? And guess what? The subscript of the anion was the charge of the cation. So you can use as use that as a kind of a guideline. You didn't hear that here. Some people, well, it's just just some further information that you can see the trend. All right, to help you out. So the formula for calcium nitrate is 3 calcium and 2 nitrites. So the point there is to determine a common value for the ions. All right, let me do this one. We got aluminum, excuse me. Aluminum is one of those plus, it's a +3, so it's in group 3A. And the chlorides are all in group 7. They become a -1 charge, okay? Here we need 3 chlorides for every +3 aluminum. So its formula becomes AlCl subscript 3, okay? And then zinc is a +2, okay? The iodide is a -1, just as part, it's a halogen. Okay, here we need just 2 iodides to cancel out the +2 for the zinc. Okay, now, remember when we talked about this? I showed you 16 metals that their oxidation state is constant, doesn't change, okay? The other metals left over, other than the metals minus the 16, all have a variable oxidation state. So therefore, we have to tell you, in this example, what that is. In this case, we have to write a Roman numeral, and that Roman numeral tells you what the charge is on that metal. So a +2 right here tells you you're dealing with copper +2. That's Cu, copper +2. The oxygen, which is oxide, is a -2, okay? And so it's a straightforward, like number 2, magnesium monoxide. It's a straightforward 1-to-1 because both of the anion and the cation are equal in magnitude and charge, just different magnitude. I just say one's a -2, one's a +2. So all we need is a one of each. So its formula becomes CuO, okay? All right, let me clear this up a little bit. Come back to the names here in a second. Here we have lead, Roman numeral 4, okay? Lead, Pb, Roman numeral 4. That tells you that you're working with a +4 ion, okay? And now remember, this Roman numeral that you find here has nothing to do with the Roman numeral on the periodic table. Nothing to do at all. There's no relationship here. All that Roman numeral is telling you what cation, what charge you're working with, okay? Because these are the metals that have a variable oxidation state, and you have to be told what they are, or you can calculate it. I'll explain that here in a second. We know the oxygens are -2. All right, so therefore we simply need 2 oxides for every one of the lead +4. Okay, so its formula becomes PbO2. PbO2. All right, let's go over the names for a second. So in this case, what we did was you were given the element. From the element, you converted those 2 ions, okay? Or you were told what ion you're working with. And from the ions, you're able to put them together with sufficient cations and anions so that when they combine, they end up with a net charge of 0. And that's how we came up with these formulas. Now, with respect to the name, remember the metals, its name stays the same, okay? So Na remains as sodium. So it's sodium, and then sulfur becomes sulfide. So the name here is sodium sulfide. Okay. We got magnesium. Oxygen becomes oxide. Okay, we got potassium. P is phosphide. Okay, then here we got calcium nitride. And then we got aluminum chloride. Okay, then we got zinc iodide, IDE. Now, we're working now with the variable oxidation state metals. And so again, that's why you're given that Roman numeral. So you're dealing with Roman numerals, you're going to use it to name it. So Cu is copper, you're right, copper. And then the parentheses, Roman numeral 2, okay, oxide. Okay. Next one is lead, Roman numeral 4, oxide. Okay. Notice for the others that we just did, we use no Roman numerals for them. Okay. Why? Because they are part of the sweet 16, as I call them. Okay. They're part of the 16 that have a constant oxidation number. Okay. It's not variable. And therefore we know all the time what charge they're going to be. So therefore we do not use Roman numerals for those 16. So it wouldn't be sodium 1 sulfide, simply just sodium. Those other ones, number 7 and number 8, are the variable metals. So therefore we have to tell you, we would tell you what charge you're working with. If you didn't know what it was, okay, you'll be told in the name, like I just wrote copper 2 oxide and be asked to write the formula. Well, that 2 Roman numeral belongs to the metal. So that tells you you're dealing with copper 2. And so from the name, you convert them to the ions. Okay. And that allows you to write the formula. Okay. All right. Sometimes you're given the formula. Let me erase all this. And you're asked to determine, okay, what is the name? Sometimes maybe you're given this. Okay. And let's assume you didn't know all this information there. Well, recognize that copper is not part of the 16. So dash your flag and tell you, oh, I'm going to need Roman numerals here, but I need to know which one. So the base name would be copper. And you know it's going to be a Roman numeral of some kind. Oxide, that is the base name. That is not the full name. Copper oxide is half the name. You got to know what the Roman numeral is, okay? And let's assume you, like I said, I'm erasing that you didn't know. Well, we back calculate. We know that the oxygen is always a -2, okay? And it has to combine with, we only got one copper here, so I write a very generic and very quick algebraic equation. Cu is copper, okay, plus a -2 equals 0, right? So that means that copper 2, we saw for copper, has to be a +2. So what number plus a -2 gives you 0? Obviously a copper 2. So that's what I mean by back calculating. Once we back calculate that, we determine you're using copper 2. Now we know what Roman numeral to use, okay? So like I stated, you're always going to know the oxidation state of either the cation or the anion. And knowing that, even for example, what we did earlier was the sodium nitride. Let's say you forgot that the nitride was a -3. Well, you do know that the sodium is group 1, and that means there's a +3 for every 3 for the 3 sodiums, and that plus whatever charge that equals to equals 0, plus the charge of the nitrogen, in this case the nitride, equals 0. So what number plus 3 gives me 0? Obviously a -3. Okay. So you see how that works? Now, I'm going to give you a general formula. I said earlier, the cations plus the anions equals 0. Sometimes the molecule may not equal 0. And so a more general equation would be the number of cations plus the number of anions should equal the charge of the molecule or whatever it would be. 9 times out of 10, it's equal to 0. But occasionally, like the polyatomic ions, it's not. You know, let's say you got NO3 -1. And you might be asked a question, and there's some homework problems like this where they're not using specifics, but they're giving you generic formulas, right? You might be asked, well, what is the oxidation state of this nitrogen? It is not -3. Why? Because it's bonded to oxygen. If it was just nitrogen by itself, yes, it would be nitrite -3. But in this scenario, it is bonded to oxygen. So it's really going to have a different oxidation number, oxidation state. So we can set up that equation here as follows. We know the overall charge is a -1, right? Overall charge. We know that the oxygen is always going to be a -2. The oxides are always -2. There's 3 of them. So -2 times 3 says overall you got a -6. All right. And then you can write your algebraic equation where you got nitrogen -6 equals -1. Okay. So now I can solve for nitrogen. So I got nitrogen where I got 6 minus 1, right? I moved the -6 over to the right, gives me a +6 in the right, and that equals a +5. So in this state, nitrogen has a +5 oxidation state, okay? Because it's bonded to the oxygen. So the whole point of this exercise is this generic equation here. Yes, the book talks about is equal to 0. And like I stated, that's, 90% of the time, that's a true statement. But occasionally you have things like the polyatomic ions where you're being asked, what is the oxidation state of the central atom? Okay. And if that's the case, you will know what the oxidation state of whatever bonded to the central atom, the oxidation chart, the charge for the whole molecule, you can solve for it like we just did. Okay. So this general equation gives you a lot more latitude with respect to doing the calculations of the oxidation state of one or the other, the cation or the anion. All right, so we went over the names. Okay, so point here, every time you put a metal and non-metal together, make sure you check for the charges. Okay, you want to make sure that you're using the correct oxidation state for the metals. Okay, and then you put enough of them so they add up to equal 0. Okay, now what about the polyatomic ions? So how do we utilize those? Well, let's figure this out. So same thing, the only difference is now you're given the polyatomic ion and you're asked to write a formula. And you know the charge, you're given the charge. So in this case, you're given the OH negative. If you go to the polyatomic ion table, that guy is called the hydroxide. Be familiar with hydroxide. We're going to use a lot of that in the next chapter. Okay. So we have here the magnesium metal that we want to figure out what is its oxidation state. And so obviously it's in group 2, so it will have a +2 charge. We're told already we got the OH negative, the hydroxide. And so the polyatomic ion has a -1, so we need 2 of them, okay? Well, the fact that we need 2 of them means that for these polyatomic ions, and you have to recognize that's what you're working with, you have to use parentheses. So it becomes Mg parentheses OH and parentheses subscript 2. Okay. And that is how we write this magnesium ion and hydroxide. Since we need two of them, it would be incorrect to write this O2H2 because that I have no idea what that is. That is not the species we're working with. Okay, it's a polyatomic ion, as I stated. If you need more than one, you put a bracket around a parentheses. Okay, so the formula becomes MgOH, well, parentheses OH and parentheses subscript 2. That is called magnesium hydroxide. Okay, here's the next one. We got the phosphate. Okay, so this is magnesium hydroxide. Take a look at the polyatomic ion, you'll find it there. That's its name, hydroxide. This one's called the phosphate. Okay, so and we know that's going to be potassium. So its name will be simply potassium phosphate. Okay, we know that potassium will have a +1, and that means we need 3 of them because the phosphate has a -3 charge. So its formula becomes A subscript 2 PO4. Now you only need one polyatomic ion, the phosphate. You don't put parentheses around it. Notice it's just simply PO4. Okay. All right, next one. We have silver. Okay, and this is called the sulfate polyatomic ion. Silver always has a +1. It's one of the 16. Okay. The sulfate has a -2, so that means we need 2 silver ions. Okay, so its formula becomes Ag2SO4. Again, one polyatomic ion, no parentheses. Okay. Okay, here we go. We have calcium, and then we have, I'm writing the name as we go along. Calcium nitrate. Okay, check your polyatomic ion table, you see it. Nitrate, not nitride, nitrate, because you got nitrogen bonded to oxygen. Okay, potassium has a +2. The nitrate has a -1, which tells you I'm going to need 2 nitrates, okay, to cancel out the +2 of the calcium ion. So now our formula becomes Ca parentheses NO3 and parentheses subscript 2, or calcium nitrate. Okay, now here, if you look at this one here, we'll go ahead and write the name. I'm running out of space. This is copper, Roman numeral 2 carbonate. Okay, the Roman numeral 2 tells you you're dealing with +2 ion. Okay, the carbonate has a -2 on it, so it's a simple 1-to-1. Okay, so we just combine them together, and that's our formula. Copper carbonate. Copper specifically, copper 2 carbonate. If you just write copper carbonate, that's incorrect because it could be copper 1 carbonate or it could be copper 2 carbonate. See? So you gotta use the Roman numerals to distinguish which one you're talking about. All right, then point here, remember to use parentheses when you need more than one polyatomic ion. Okay. Now, naming them. We've been working with writing formulas. Now, the thing I forgot to tell you here, let me go back up and do another batch here. Yeah, see this batch here? You can mix and match, all right? You can take the sodium and hook it up with the nitric oxide, sodium with a phosphide. okay? Sodium with the nitride, sodium obviously with the chloride or the iodide. Okay, we did the oxide already. You can do the same with magnesium phosphide, mix and match. So you're starting to build up your database of compounds. And you're not limited simply to the way it's written here. You can see that you can mix and match. Magnesium here with the phosphorus, the nitride or the chloride, right? Or the sulfide, et cetera, et cetera. Okay. You probably build up already a couple of hundred molecules already. Okay. The same is true with these. Okay. You can easily say magnesium phosphate, magnesium sulfate, magnesium nitrate, magnesium carbonate. Okay. And the same with potassium hydroxide, potassium sulfate, potassium nitrate, potassium carbonate, and the same thing with the calcium and the copper, okay? So now you're probably up to about 300 or 400 different compounds you can start putting together. And these are just the metals we put up here. Don't forget you have all these other metals that you can mix and match, right? So now I've been doing this as we've gone along, but your textbook now talks about naming ionic compounds. Okay, naming an ionic compound. So the name depends on whether the metal is a fixed or a variable charge. That's that simple. Whether we use the Roman numerals or not, basically what it amounts to. The name itself doesn't change for the cation. Sodium still is sodium, be it an element, be it an ion in all the metals. So, for example, we got NaCl, okay? As I mentioned, it's sodium chloride because we're dealing with the ion chloride. All right. Bear with me for 1 second. I need to pause for. Okay, my apologies. I'm back. All right. So with fixed charge metal ionic compounds, as I stated, the fixed charge, we don't use Roman numerals. We just tell the metal what it is. The anion, I mentioned that also. The anion goes from whatever its name is to the IDE. So chlorine becomes chloride. Okay. So NaCl would be sodium chloride. Okay. Here we have this one. We have potassium and then Br, which is not bromine. The fact there's potassium in front of it tells you it is an ionic compound. So we got a metal and a non-metal. Okay. And so bromine changes to bromide. So its name is potassium bromide. Okay. And keep in mind here, it could have easily been sodium bromide, lithium bromide. Okay, all the group 1 metals and the group 2 metals. Here we have magnesium. We've done this one earlier. I gave you the name is oxide. Oxygen becomes oxide. So its name is magnesium oxide. And again, we can mix it with sodium oxide, potassium oxide, so on and so forth. Here we have calcium chloride. Chlorine becomes fluoride. There are two fluorides because calcium is a +2, right? And each fluoride is a -1, right? Prior, let me back it up just so you can see that, and I'll write it up on top here. The bromides are -1, and potassium is a +1, so it's a straightforward 1-to-1, right? Let me change the color a little bit. The magnesium was a +2, and the oxides are a -2. So again, you can put them together 1-to-1. The calciums are +2, they're in group 2, and each fluoride is a -1. So therefore, I need 2 of the fluorides to cancel out the +2 of the calcium. Okay. Its name is simply calcium fluoride. Notice no Roman numerals, okay? Because these are fixed charge fixed charge metals. Fixed, that's at sweet 16 I showed you on the periodic table. Group 1, group 2, and then 4 more. Okay, next one, lithium sulfide. Okay, is the name. Now, why 2 lithiums? Well, because the sulfides are a -2. Okay, and each lithium is a +1, excuse me. And I need 2 of them to counter the -2 of the sulfur. Okay. And we have silver chloride. Okay, because silver is a +1. And the chlorides, as we've been showing you, all the halides become an ide, or -1. Okay. So this name is silver chloride. All right. So notice also something about ionic compounds. Ionic compounds do not use any prefixes. Okay. No prefixes like di, tri, etc. Unlike covalent compounds, when we have the formula, this one is carbon dioxide. Okay, and that's a big difference here. Ionic compounds, no prefixes. Covalent compounds, yes, prefixes. Okay. So that means that this would not be, for example, number 4 would not be dilithium sulfide. That would be incorrect in naming. Okay, nor would it be calcium difluoride. That would be incorrect. And you will see sometimes if you start reading the labels of items you use in cooking and so forth, from just reading the labels, you see a lot of salts. Sometimes they use the di and the tri and so forth for ionic compounds, which is totally incorrect. I don't know why they do that. Maybe it's a marketing thing. I don't know. But from a scientific standpoint, prefixes are not utilized. Again, no Roman numerals here, okay? Because these are fixed charge metals. And you might refresh your memory. These are the ones that I got circled in red. Group 1, okay. Group 1 right here, group 2 right here, and then these 4. So aluminum, zinc, silver, and cadmium. Those are the fixed charge metal ions. Everybody else has variable charges, and we use Roman numerals for those. Okay. Also, keep in mind, you can mix and match. So potassium with oxide, potassium with fluoride, okay? Potassium with fluoride, potassium with the sulfide, potassium with the chloride. And then the same is true with magnesium bromide, magnesium fluoride, magnesium sulfide, magnesium chloride, etc., etc. Okay. Oh, mix and match here. Now, with respect to polyatomic ion, the name doesn't change, okay? So be familiar with the polyatomic ions. They're over here in the bottom left. They have their own specific name that doesn't change. So NO3, I've seen this a few times. NO3 negative is nitrate. It is not nitrogen trioxide, okay? Because first of all, it's a polyatomic ion. If it was a covalent compound with no charge, yes, that would be a nitrogen trioxide, but here it's not. It is simply nitrate. And the same is true for the NO3. It's for all of these polyatomic ions. And they have their own specific name. Even though they are covalent compounds, they are ionic, okay? In ionic and overall nature. And I'll explain when we talk about acid-base reactions, why these guys start off as ionic and become polyatomic ions. All right, so with respect to this, the point is you might look at this and you say, well, we know this is potassium, okay? And so we can simply write potassium quickly. And then, it's the first time you see this, you see phosphorus. And you might think phosphide, okay? And that would be true if it was simply this, okay? This would be definitely, no questions asked, potassium phosphide. Okay, because remember the IDE extension means it's just the element itself, the suffix. But right next to it, we have phosphorus bonded to oxygen. So now that should send a flag and say, oh, I'm talking about polyatomic ions here. Okay, so he sends you to the table and look for a PO4. Now you might furthermore, you could say, all right, well, that's a polyatomic ion, let's verify that. Because I know potassium each have a +1, but there's 3 of them here. So that means I got a +3 for all the potassiums total. That infers that the PO4 must be a -3. And so when you go to the polyatomic ion table, you look for PO4 -3. And there it is right here. PO4 -3, and that is called phosphate. Okay. Okay. And again, just to reemphasize, I see the potassium, I see phosphorus, thinking it could be phosphide, but right immediately I see oxygen. That indicates to me that I have a polyatomic ion. Check the table. That is phosphate. So its name is potassium phosphate. Okay. All right. Well, what's flagging me here? The fact that I see parentheses flags you to polyatomic ions. Okay. And so OH. Okay. Furthermore, I know that potassium is a +2. That infers, since I got 2 of these OHs, whatever they may be, each one must be a -1. So there's 2 of them to give me a total -2, right? So I go to the polyatomic ion table, look for the OH, must be -1. Sure enough, here we go, right here. And that is called the hydroxide, okay? Hydroxide polyatomic ion. And so now I can name this as calcium hydroxide. Okay. All right. Same scenario. Again, I'm going through a systematic approach because I realize this is the first time you've seen these, and this is how I would attack the problem, right? So I got zinc, so I know that's the name, the metal. I got sulfur, like I'm thinking like up on top. The first one I got sulfide, but can't do that. Why? Because right immediately afterwards, I got oxygen bonded to that sulfur. Okay. So that sends me to the polyatomic ion. I know that table. I know that zinc has a +2. So this SO4 must be a -2. It has to be a -2. SO4. So I go to the table, look for SO2 -4, and there it is right there. SO4 -2. It is called the sulfate polyatomic ion. Therefore, its name would be zinc sulfate. Again, notice no prefixes for the metal because these are fixed charge, fixed oxidation states. Okay, fixed oxidation states. And furthermore, mix and match. I could easily make potassium hydroxide, potassium sulfate, calcium phosphate, or calcium sulfate, And the same with zinc, zinc phosphate, zinc hydroxide, etc. Plus all the others that we talked about so far. So we're building up quite a bit of a database of chemical names. Okay, with the variable charge, you write the metal name and then in parentheses, the charge for that species, whatever the charge is, and then the non-metal, which is with the ID ending, okay? And question is, well, how do we know which one we're doing? Well, first of all, I know that the parent name will be copper. And I know that I'm gonna have, it's a variable because copper is not part of the 16, so that tells me put a parentheses there. And then I got chloride. So the parent name is copper chloride. What I don't know is what's in the parentheses, but I can calculate that, okay? And I calculate that because I know that each chloride has a -1, and there's 2 of them. So that means I got a total of -2. In this case, the charge is equal to 0. The total overall charge is equal to 0. So I got Cu minus 2 equals 0. Simple algebraic equation. You know, what number plus a -2 gives me 0? Obviously, it's a +2. Okay. So in this state, copper must be copper Roman numeral 2. And that's how I calculate it, because it's variable. I always gonna know if it's the variable charge metal, I'm gonna know what the charge is of the anion, okay? Either in the single state or in the polyatomic ion table. You know, this could have been easily SO4, copper sulfate, CuSO4. Well, I don't know what this is charge-wise, but what I do know is this polyatomic ion has a -2. Again, that equals a 0, so that means that copper must be a +2. So in this case, I got copper 2 sulfate, okay? If I was using sulfate. So whether I'm using a single anion, like the chloride, or a polyatomic ion, I'm going to be able to know the anion's charge, which allows me to calculate what the cation charge would be. Okay. All right. So its name is copper 2 chloride. So let's take a look at this. All right. So we have lead, we know, so we can write the parent name. We know it's lead. We know it's not part of the 16, and oxygen is oxide. Okay, so that I can write down. I know that part. Question is, what goes in the parentheses? Well, I'll calculate it. All right. I know that each, and it's going to equal to 0, okay, this total charge. Each oxygen is a -2. I got 2 of them. That means I got a -4. And so lead minus 4 equals 0. That tells me that lead must be a +4, has to be in this combination here. So that name becomes lead Roman numeral 4, IV. Okay. All right, let's take a look at this one. All right, we have the parent name again. We know it's nickel, parentheses, and then a bromide. Okay, we know that much. We don't know what's in the parentheses. Again, nickel is not part of the 16. That's why I got a parentheses. All right. We know that the bromides each have a -1. There's a total -3 there. That infers that nickel must be a +3. So this becomes Roman numeral 3. Nickel, Roman numeral 3, bromide. Okay. And, oh, sorry. The sulfates, And we'll work it through. We got sulfur. And then immediately following that is oxygen. So that sends me the polyatomic ions, okay? And that's a -2 for the sulfate. That infers that manganese here must be a +2. Okay, so Roman number 2, manganese, not magnesium. That can get confused a lot. Mg and Mn, two different species, two different elements, okay? This is manganese, not magnesium. All right, so it's manganese, Roman numeral 2, sulfate. And then here we have copper. Okay. And so the parent name, we can write copper, parentheses, and then NO3. NO3 sends us polyatomic ions. We have nitrate. Okay. The nitrates are all -1. And so that means that this is copper 1, +1. So Roman numeral. Okay. So this name would be copper 1 nitrate. Now, if we had, using copper, if we had this species, okay, that would be copper, Roman numeral 2, nitrate. Okay, because there's 2 nitrates here. Each one has a -1, so there's a -2. Okay, equals 0. So I have this copper must be a +2 under this formula. Okay, so you see the difference between two, copper 1 and copper 2? Totally different species, okay? Total different properties, and we have to distinguish which one we are using. And as I mentioned before, this Roman numeral prior to that, it used the ending cupric and cupris, and that was very ambiguous at times. So Roman numerals kept it simple here, straightforward. Here we have cobalt. Now notice something here. We have a nitrogen. There's no oxygen afterwards, right? No oxygen after the nitrogen. So automatically it's the single element. So that should tell you that you are dealing with nitride. Note the difference here with the one we just did up here. Immediately following the nitrogen, we have oxygen. That's the nitrate. No nitrogen and no oxygen after the nitrogen. It's the nitride. Okay, that means that that has a -3. So that means that cobalt must be a +3, has to be. Okay, so that's a Roman numeral 3. Has to be, because when we put them together, we want them to cancel out. Okay. And then, a little bit of a challenge, but we can still work with it. Here, let's break it down. We have iron, and this is carbonate. It's a parentheses. Okay, parentheses should tell you, oh, polyatomic ion. Go look at the table. CO3 is a -2. Let's go find it. Okay, CO3. -2, excuse me, right here. Okay, that's called the carbonate. Okay, the carbonate polyatomic ion. All right, so what do we know up till now? We got the iron, parentheses, and then carbonate. That's the parent name. We know that each one has a -2, okay? And there's 3 of them. And so the algebra, there's also 2 irons, so I can make my algebraic equation as 2Fe -6 = 0, okay? The carbonate is, each one is a -2, and there's 3 of them. So 3 times -2 is -6. There are 2, look at the subscript of iron. There are 2 irons. So there's 2 Fe. So what I need to do is solve for Fe, iron. So I can rearrange this. So I got 2 Fe equals 6. Divide through by 2. That means that every iron is equal to a +3. Okay, so we are at this stage, we are working with iron 3 carbonate. Okay, let me rehash that one more time. Okay, we have iron carbonate. Okay, we can write the parent name down. The question now is which iron we're working with. Well, we're going to work it through and generate our generic algebraic equation, which is this. Each carbonate is equal to -2. I got 3 of them. Okay, so I got total -6. I got 2 irons, so I can rearrange this equation so it tells me that I'm working with iron 3 in this scenario. Okay, so that's the way to work that out. Earlier, I stated that the charge of the cation is the subscript of the anion, right? Remember that? And just look at the subscript of the anion. Isn't that a 3? So you can very quickly at a glance determine what iron you're working with. But if not, you can go through the scenario here of figuring it out, what it is. Okay, let me clear up this mess here. And what we have here is, name-wise, iron 3 carbonate. Okay. Again, as we did earlier, you can mix and match. We can go lead bromide, lead sulfate, lead nitrate, lead nitride, lead carbonate, and the same with nickel, nickel oxide, nickel sulfate, nickel nitrate, excuse me, nickel nitride, nickel carbonate, et cetera, all the different combinations. Okay, so you again, you're probably up 600-700 compounds you can probably put together. Okay, all right. So in this scenario, you're being either asked to give the formula and the name. Okay, so give the formula and the name. And to do the first one, well, we got to find strontium first. Okay, strontium is a metal. It's in group 2. It's element number 38. Okay, and that's a +2 right here. The hydroxides here are OH negative. So that means I need 2 of them. So our formula would be SR parentheses O2 hydroxides. Okay, 2 hydroxides. Strontium hydroxide. Let me stop it here. I'll just check the time. You know? So let's stop it here on chapter slide 17. And we'll definitely be done with it next time. All right.